Okay, so this is distributed systems. It's about distributed programs. So anybody want to define what a distributed program is, as opposed to a non-distributed program? So what might be a litmus test to distinguish between distributed and non-distributed program? Yes?
A distributed program that has some form of communication between usually like different hosts, like multiple, I guess potentially could be on the same system, but there's some kind of separation between like processes and things that are happening that's not done in a sequential manner. Separated along.
Okay, great. You said a lot of things, and all of which are correct. So you're saying it can run on multiple computers, but we don't know which set of computers it might run on, which could mean that it could run on a single computer also. So then the question is, how is a distributed program different from a non-distributed program that also runs on one computer? And you said the difference would be some kind of separation.
Yes, things aren't necessarily running sequentially. There's like a program that's separated and processed in, like I said, not necessarily in a linear manner.
Okay, so there is some kind of concurrency, and you can get concurrency, those of you who've done operating systems, through threads. But you don't use the word thread, you use the word process. So is that something you really meant? You were using the word loosely? Or actually, let me give the answer pose the question to other people too. So he used the word process and not thread. Was that accidental or was that intentional? What do you guys think? If I say it's yes.
Probably, I think most important problem when you're designing distributed systems is probably has to do with the shared resource being an important aspect of design. So if you think if you have a system where you call a program running on multiple physical computers that shares a database, say, I think that would be a distributed system. And by analogy, just two threads sharing some memory process could also be a distributed system in a way.
So you're saying basically it's the same at an abstract level they're the same. They involve multiple concurrent agents sharing some resources, whether the resources are memory in a shared memory or whether they are a shared database.
Sure, I mean, if you have two separate threads with some shared memory, right? Or let's say we have two separate processes in the same computer that share some medium disk that they use as memory. Assuming, let's say they have no RAM for some reason.
So you're saying.
In this case, it's the same.
So given that abstraction, you think in both cases we should call them distributed programs.
Well, maybe it might not be helpful to call them distributed programs because it seems like this is really more of a. I don't think there's much of a real distinction there.
Okay. And anybody want to disagree with that? Yeah.
I think the distinguishing factor is communication between two entities, such as processes or separate hosts that are seen somewhat as independent, and therefore they need to have some method of communicating so that all of the hosts or processes are on the same page.
So you're saying, look, you need some form of communication among processes.
Right. Whereas if you have like a shared resource, every entity has access to that resource, and therefore there's not as much of a need to communicate that information.
So you're saying that you just have the shared memory, and there's no notion of explicit communication,
Right.
but it's done through shared structure. Okay, so you think there's a difference. Okay. Anybody else want to weigh in on this? Yeah.
Even if you have, let's say you have two processes, two separate computers which communicate their use of some shared database or some other shared exclusive resource through they have some other channel to pass messages about who's using this resource. This is completely analogous to you have a memory, you have an index that's in the relationship with the lock to control access to this resource. They need to communicate in order to, maybe not in every case, but in the most non-trivial programs, you're going to have some kind of communication and control that uses the shared resource. I mean, the OS might provide abstractions for that, but.
Okay. So we've got both viewpoints. If you go abstract enough, so what's your name again?
Oh,
Ulrich? Ulrich.
Yeah.
So if you go abstract enough, Ulrich is right. And if you say, look, in one case you have a network, and in one case you don't have a network, then, sorry, what your name was? Dylan. I'm going to forget, but I'll try to remember, okay? Then Dylan's correct, okay? And did you mean processed accidentally? Or, I mean, which side do you take? You started the whole discussion.
So in operating systems, Dr. Jaffe made the distinction between a process and a thread. And thread, in the sense, like Dylan was saying, that we do have a shared memory resource.
Yeah.
So for example, in our class, the Java virtual machine is run in some process, but then the Java virtual machine shares up spins up multiple threads, which all share that memory space that the process has been allocated.
Yeah.
So there is a distinction. Yes.
So at the underlying implementation level, there is a distinction. Okay. At the conceptual level, at the algorithms level, maybe there is, maybe there isn't. Even at the abstraction design level, maybe there is, there isn't. And when I said maybe this way or that way, there's been a schizophrenic, research direction that sometimes they go and try to unite these two concepts, sometimes they have to separate them. And so, like I said, you're both correct. Okay. So distributed program, a program involving multiple computers, and specific computers must be bound at runtime. You don't go and say this program runs on these 3 computers. So if the binding is at runtime, you can probably run them all on the same computer also. And so then you have to talk about processes. And so how would you define a process? I mean, this is, for those of you who don't OS, that's trivial. Well, almost anyone is trivial, but let's just make sure that we're all the same. So what's a process? How would you define it? Maybe it's not so trivial. No definition is really trivial, actually.
Well, I think a good process would be described as like an OS level abstraction of a single task that's being performed by one computer. So it would be like running a single program or something like that, where it takes up, it gets its own share of memory and its own share of like processor quanta in terms of processing time. And then, sort of that's the context in which a process, like the 2 main resources that a process runs with.
And so how is the process different from a thread now?
Or a thread.
Yeah, let me take it. Yeah. I think you gave the answer already, but let me get it from it.
Typically, when you're doing context switches between processes, you have to copy all of the contents of the registers of the processor and the entire process control block, all the memory, state of execution, everything in there. But with threads, you only, since you're using a shared memory space, you no longer have to copy the entire contents of the process. You can only copy the contents of the registers of the processor when switching between threads. And so it allows you to multi-program, but kind of have what's the best way to describe this? Be able to switch between something with very low overhead.
Okay, so in general, so as has been already indicated, threads share memory. Processes are different, have different independent memory. That's the key. Context switching, yes, indeed, thread switching is quicker than process switching, but you don't really copy memory around when you do process switching. What do you guys do? How do you go from one memory space to another memory space?
There's a virtual memory mapping.
So
you
there's
just
page
change that
table,
mapping, yeah.
the page table register just changes. Okay, so but the same, your TLB remains the same. So then you're within the same process, so you get much faster execution for that reason. Okay. When you fork a new process, then if the program doesn't already exist, you have to copy it. Okay, but when you switch between processes, you don't have to. You might have to bring some pages over just because they're not resident in memory, but it's not required. It may happen. Okay. So program, when I teach 401, I say it's an execution instance, an executing program. Okay. And from an OS point of view, that it's a piece of memory with a stack. Well, the stack is associated with the thread, but it's one or more stacks. Okay. And the program can result in multiple processes, and you can see through all kinds of interfaces what the processes are, and these processes interleave. Okay. And so do threads, but threads are independent activities within a process, associated with they're typically associated with a process, but they have their own stacks. Okay? So a thread is basically a stack in a process. So what are we talking about? Are we talking of we're talking of distribution, so we're talking of running on different computers possibly. So you can distribute processes. You can have one process executing on one machine, another process executing on another machine, and hence you have a distributed program. And the way threads are implemented, threads within a process do not run on different machines. Okay, so all threads in a process run on the same machine. So whether at an abstract level, there's the same issues we won't get into, but at an implementation level, there's a difference, and so we're talking of inter-process communication also. Okay, so let's get to that. If a program forks two processes, two or more processes, would you call that a distributed program? Is that sufficient?
I think the execution of one should probably depend in some way on what the other is doing.
So a shell keeps forking a lot of processes. We don't think of a shell as a distributed program. The shell is trying to isolate the programs from each other, ideally. So the key is some kind of coupling, okay, and some kind of connection, okay. So if there's a pair, then you say that the input of one should depend on the output of another. If you have n processes, how would you define the coupling? What kind of coupling are we expecting? So if the program has two processes, one process should depend on at least. Both could depend on each other. In the case of n processes, how would you generalize from 2 to n?
At least n minus 1.
Sorry?
At least n minus 1.
So each process, induction, right? So each process should depend on n minus 1 other processes. And yeah. That sounds good. Anybody else want to? Yeah.
Do we essentially control of how they communicate it? Send the data out to the other processes, so they're not all trying to communicate with each other, but maybe communicating to some subset of the processes that are not necessarily distributed.
Okay, so I didn't get into this in my slides. I had it actually from previous lectures, but there's logical connection and physical connection. Okay, so I could be logically connected to another process, but we could be routing all the communication to some other process. And you're saying maybe that's good, right? And anybody else want to offer a definition for n? So you want a connection could be direct or indirect. Okay? So we didn't, when you said n minus 1, it's not clear whether each process should directly depend on n minus 1 processes or directly or indirectly. So we can draw a graph. So what you don't want is two processes independent of another two processes. Then that's not a distributed system. So you want them all to be connected in a graph. And so that's sort of what I have here. So each process is coupled to at least one of the processes in the group, and more importantly, when you create a graph by drawing links between connected processes, that's not partition. Okay? So that I think would satisfy what everybody wants. Okay? So distribution versus concurrency, the way we've defined it, okay, you can have processes with no fine-grained concurrency. Okay? Theoretically, you can have a process, each process has only one thread. If these two processes talk to each other, that's a distributed program. Okay? And a lot of the threads are relatively new in many domains. So a lot of distributed programs were written this way. No, there was only one thread, and each process, and they were talking to each other. You can have concurrency and no distribution. Okay. So, but typically, in modern systems, you're going to have concurrency and distribution together. Okay. And since you do have independent units interacting with each other, the subject matters are quite related to each other. Okay? So by learning about distributed systems, you will also learn much more about concurrent systems. And the reason why you typically have it this way is has to do with software engineering. That you don't want one process to be when you have only one thread in a process, that thread it's like an OS scheduler. It's scheduling multiple activities, and you don't want OS-like functions to be implemented by each process, so you just have multiple threads. So you'll have at least one thread that's receiving messages, and you may have more than some other thread or multiple threads sending messages. Okay? So you don't have the receiving thread, the thread that directly receives a message, also send messages to it. So you will have multiple threads, and you'll see that. So one of the things you guys will learn a lot about, if in OS you've learned how to implement threads, and you're going to learn how to harness threads a lot in this course. Okay. Questions so far? So non-distributed creates a single process unconnected to any other process, must deal with sequential and possibly concurrency issues, creates a pair or larger group of connected processes, and must also deal with distribution issues which are related to concurrency issues, but must also typically also deal with fine-grained concurrency issues. Okay? So if you like threads, and if you like fine-grained concurrency, you'll see a lot of it here. Okay? So lots of you said that, look, cloud computing is a buzzword. I want to know more what's going on underneath. Lots of my friends told me that distributed computing is important in general, or maybe this particular course is important. So, a lot of you said that I'm a practical person and this sounds like a practical course. So what are some examples of practical distributed programs that you think of? Yeah.
Well, big data seems like a good example. Like, you want to, like maybe the data won't fit on one machine and it exists on hundreds of machines, and you want to run it all at the same time and not wait.
So big data, which is a big deal nowadays, that requires lots of processing.
Yeah.
So maybe one computer is not enough.
Yeah.
It requires a lot of storage. Maybe one computer storage is not enough. So that that's certainly an interesting application. Yeah.
Maybe if you're trying to provide like a kind of a web service or something that's available to the public, then you can just connect to a single machine and maybe use a distributed system to perform a complex calculation on many machines that wouldn't have been able to have been accomplished so quickly on a single machine.
So you said two things. One is that there's a calculation that you can't do in one machine, so you want to do multiple machines, which may or may not involve large data. Okay. And the second thing you said was that certain services maybe you want to access remotely. Okay, good. Other examples?
Basically, the whole internet is a distributed system. To load a web page, you have two different machines cooperating to sort of a shared goal. And so whenever you're doing basically anything, it's behaving as a distributed system.
So whenever you're doing anything on the web, it's behaving like a distributed system. Yeah.
DNS would be a good example.
DNS supports distributed system and is self a distributed system. So that's one of the nice things. So, distributed computing, a lot of the abstractions you see today were invented by OS people because they wanted to write distributed operating systems. And so their design is influenced a lot by file systems. They wanted to write a distributed file system, which is sort of a web system you can think of as a wide area file system. So, other examples? So, like you said, the harder question is what's not a distributed application. Everything else you can imagine, any computation, any functionality that you can imagine, you might want to present as a web service, so it becomes distributed. Okay, and it may involve complex computations, and it might have large amounts of data, and so, in today's world, it's hard to answer the question what should not be distributed, and the only reason to not distribute something is security. Okay. So, because if you want to run everything on one machine and you don't trust other machines, and if you study security, there's all kinds of covert channels even on a single machine, and the moment you send data over the network, you're leaking more information. Okay, so gated communities are more safe, right? So that's probably the only reason to not be distributed. Okay. And there's distributed repositories, big data, there's remote services, so some of the initial research was on providing remote printers, remote files, My own interest is from collaborative applications, shared desktops, shared models rather than the views. Distributed sensing, you've got a lot of sensors, you want to predict whether there's a disaster or not, that's distributed computing. All kinds of algorithms, trying to figure out whether there's life outside Earth, that requires a lot of computers. So there's just a whole lot of examples. Okay. So given all the and each of these domains can deserve a separate course. Okay. There's a lot of richness in each of these domains. So what do we do in this class is the question. Okay. And to answer that question, I wanted to get a bit of an idea of what had excited you, so I can relate that to what we will do. So we will try, this is an undergrad course and this is a general course, so we'll look at domain-independent foundational concepts. So we're not going to focus on a particular domain. We're not going to focus on OSs, design of OSs, even though OSs play a big role in how distributed abstractions are implemented, even designed. So we look at foundational concepts, and I put that in quotes because that requires some explanation. And so, what's at the intersection of these? Now, a distributed program, anything that's foundational to a non-distributed program is also foundational to a distributed program. Okay? If you can't write a process, you can't write a distributed set of processes. And so, to try to get an idea of how you might, what the foundational areas might be, let's try to understand something that we know, non-distributed programs. Okay? You guys have gone through an undergrad set of undergrad courses here, none of which dealt directly with distributed. Okay? So they all had to do with non-distributed. So let's try to classify them into areas, and then see, each of the areas whether it needs to be changed in some way to accommodate for distribution. Okay? So if I were to tell you all the courses you guys have done, and I've named a lot of them, compilers, operating systems, software engineering, program 401, nobody said 110. Nobody said 110 was the most exciting course, even though that might have been the first course you guys took. So there's CS1, there's CS2, which is 401, there's data structures, there's algorithms, we give all these names. Let's try to figure out let's try to figure out what areas these courses can be classified. So let's take CS1 and CS2, 110 versus 401. What was the difference between 110 and 401? Was 401 just more of the same? A lot of you didn't take 110, yeah?
Yeah, honestly, they seem fairly similar. It seemed like 401 was just like a continuation, though they started really focusing on object-oriented programming, kind of a new one.
Okay, but and whereas in 110, it's less focus on object.
401 has a lot of focus on design patterns in programming.
So that's the way I would say that 401 is about designing programs. Okay, it's something in between your software engineering class and 110. And 110 is more about how can you write some program to do a task, whereas 401 is saying how can you write a better program, or ideally a perfect program. Okay? And design patterns are a way to find perfection. Okay? So there is language design, and there's language design and there's program design. Okay? And you guys learned about the language, and you learned about design of the program. Data structures versus other courses, other two courses, what's the difference? And similarly, you can imagine in distributed programs, you can learn how to write a distributed program, and then learn how to design a good distributed program. Okay, so the same kind of thing applies. Data structures and 401, what's the difference?
I guess data structures, you learn how to organize the information that your program needs in such a way that the program runs more optimally.
So you learned, exactly, so efficiency was a big deal. Okay? And certain common data structures. You didn't just learn data structures for a particular application. Okay? And the focus was on optimal, and when you say optimal, you have to sort of prove optimal also. So some kind of proofs also, algorithms also, associated with them. some sorting algorithms perhaps you guys have learned. Okay? So that brings us algorithms course. How is algorithms course different from data structures course?
Algorithms just proving the practicality of.
Okay, so algorithms was more on proofs rather than implementation. Okay? So compilers and operating systems, where do they fit in with these other courses? How the software and hardware interact, right? And in fact, what about 541? Where does 541 fit into with these courses? 541 is the machine organization, right? No, that's 120. That's sorry.
Digital logic is
541 is also what is after. It used to be called 120. What is the machine organization called now? 411. Right. So let's talk about 411. 411 and other courses, how do they fit in? And you kind of answered that question.
I guess you learn how your machine is actually accomplishing the instructions that you give it.
So how the machine is doing it versus how Java is doing it. So there's sort of abstractions. In both cases, you have abstractions, and one abstraction is higher level than the other abstraction.
I think 411 is about kind of working down rather than
Yeah.
higher.
And then compilers is connecting them together. So that's implementation, right? And OS, where does that fall?
Sort of the same practice as compilers to some extent, sort of sitting between the software and the hardware.
So it's something in the software and building an abstraction over the hardware. Okay, that's shared among multiple processes. So you can take these courses, and in data structures, I'm saying the focus is on the data structures is the big deal. Algorithms is relatively small, at least provable algorithms, and what you can talk about is abstraction design. Okay, whether it's a hash table or an array that's provided by the language, or a hash table that's provided by a library, they're abstractions. And you can talk about abstraction design, and that's what you learn in CS1. How is the what's the design of the abstraction? Okay, and then there is abstraction use. What are good ways to use abstractions? Okay, you learn that in CS2, and you learn abstraction design and use in data structures. Okay, you learn hash tables, and you learn how to use hash tables, maybe in sorting algorithms. And then this implementation of algorithms and associated data structures, okay, and proofs of algorithm and associated data structures. So there's implementation versus proofs, okay, and compilers are also data structures and algorithms just for a particular domain. OS is algorithms and data structures for another domain, okay, and in both cases we involve there's a notion of layering. So in programming languages, there's high-level languages, assembly languages, machine languages, and there are assemblers and compilers. They're all called translators. They're called translators because they translate between abstractions. Okay. OS, did you guys study in OS layers of OS also? Can you guys make sense of how I've layered in OS? So there's thread management at the bottom. Without threads, you can't have thread synchronization. Now, whether thread synchronization comes at the bottom or thread communication comes, that's arbitrary. Okay? You can design things both ways. And interrupt management I've put right on top. Okay? Again, you can do interrupt management below also, but you can imagine a special thread that just is in charge of managing interrupts. Special OS thread. Okay? Networking. So a lot of you talked about the fact that you like layers. Okay? So networking, there's many ways to layer things in network. Okay, but there's the physical communication, there's the link level communication, there's inter-machine communication, and that in turn can be UDP or TCP/IP depending on how reliable it is. So we see the notion of layering, and that's where implementation typically involves translating between layers. Okay, questions so far? So abstraction implementation involves mapping to lower level abstractions. So if you want to define distributed computing in sort of a more fine-grained way, we'll say that we are not just talking about creating connected programs. Yeah, that's very general. We can take all these concepts that we know from non-distributed computing and say, let's go and apply the adjective of distributed. Okay? Distributed abstraction, design of distributed abstractions, the usage of distributed abstractions, the implementation of distributed abstraction, right? What are interesting algorithms and data structures that you wouldn't need in non-distributed programs that you would need in distributed programs? What are some classic ones? And what kind of proofs can you write? So there's a big design space. Okay, so we have one course that's going to try to do things in a distributed fashion and apply. And the question is, to how many different sub areas should we apply the word distributed and study, okay, in this class? And let me tell you what others have done. Okay, what I'm going to do is different. Okay, so typically distributed computing is not taught at the undergraduate level. Mike Ryder taught it once and hasn't taught it again after that. And last year, I was told that we need badly a senior level course to be taught at the undergrad level, and what would I like to teach? And I said, well, maybe let's do distributed computing. Mike's got a course. I did it. I'm doing it differently, but at least the idea of teaching distributed computing to undergrads is a good one, I thought. Okay. So what is done? There's a lot of books on distributed. We didn't even talk about models of computing, automata theory, Turing machines. So that stuff is also very important. Actually, when I was studying computer science, compilers and that course were my favorite courses, and they're related to each other. So there's similarly distributed models and lots of proofs. So a lot of textbooks that you will see in distributed computing are at the graduate level and deal with this. Okay. There's also some work on distributed operating systems. So operating systems is an exciting field, and distributed operating systems is more exciting. And this is sort of the practical dual of the theoretical books. Again, these are graduate levels. So what do we do at the undergrad level? And this is very wordy here, but we'll basically do a broad overview of each of these aspects. And it'll be an implementation based. Okay, so we won't be writing proofs, it'll be more like your 410 course, where you focus on, there'll be algorithms here, but we won't be proving things. Okay? We'll be implementing things. And we look at distributed abstractions, how they're designed, we look at how they're used, selected abstractions, how they're implemented. So we'll do a little bit of all. And hopefully what we do will be connected to the components we do will be connected to each other. Okay? So that's the goal. And because and by the way, the idea of teaching distributed computing to undergrads is lots of people have that idea. People just haven't agreed on how it should be done. There are conferences on how distributed computing should be taught to undergrads. Okay? So that's good news and bad news. The good news is that what you will learn is something unique. Okay? So when you go for your interviews, lots of you are seniors. You have to learn something different. Okay? But the bad news is it's not standard. Okay? And there's no textbook, and we'll see how we will overcome that problem. Okay, questions so far? So let's talk about the levels of abstraction in distributed computing. We know that in non-distributed computing we have levels of abstraction. So what might be yeah?
While there isn't a textbook, would you recommend any papers that we can read on some of the topics?
Papers. I'll tell you what I will recommend. Since we're going to be doing, so I'll talk. Let's answer that question at the end of my lecture. Now here's the question. When we were trying to distinguish between distributed computing and just concurrent computing, we said there's an underlying network, or there can be a network. Okay? So what does distributed computing, in your mind, add to networking? Those of you who learned 431, what do you expect? What additional stuff do you expect?
Well, in this case, you're going to have some kind of, if we're doing it on multiple systems and networking, we're obviously passing some kind of information, something has to be transmitted to the network, whether it's data or some kind of like control.
So you're agreeing with me that networking and distributed computing are related to each other. My question is, how does distributed computing add to network? Yeah.
Calling multiple devices for information like network information. So multiple devices are being called simultaneously to get the information.
Sorry, multiple what are we?
Endpoints.
Multiple endpoints.
Network endpoints, nodes are called continuously for traffic data being collected. So distributed system comes into this collecting data.
So, networking also connects multiple endpoints, computers together. Whether it polls or not, let's not get into that. In general, polling, as a system person, you don't want polling. As it turns out, you can't do without polling. If you've studied 411, you know that at the very interrupt level, there is cycle stealing and you have to do polling. But ideally, you don't want to do polling at higher levels. Okay? So, yeah.
I don't think that distributed computing necessarily adds that much to networking, because once you're using the distributed system to maybe do some calculation like we had said earlier on multiple computers, but once you're ready to communicate onto a network, we're not adding anything to the layers that already exist on the network side. Once you're trying to put bits on the wire to connect to somebody else, we're just assuming that all of those other layers are functioning the way that we've designed them to, and that we can add some application layer stuff for distributed systems to add on to the network layer, but we're not changing anything about the layers that have been previously designed.
Okay, so what you're saying is distributed computing can build on network.
Right.
But you're saying that, and from networking point of view, distributed computing is whatever happens in the application, right?
Right.
But I'm saying we're doing foundational things, so I'm not doing very application-oriented stuff. So we are doing something that's above the network, yet is not application dependent. Yet is not application dependent. Okay? And so what's the basis of creating such a layer? What's fundamentally different between creating a distributed system and creating a network? And I agree with you that we don't have to change the network. Okay? So there's all kinds of there are people who think that we can create a more robust lower layer, knowing what the higher layer is in general. So how would you say what would you say is the fundamental difference between distributed system and system network? System of networks. And think of the endpoints. Yeah.
Well, one of our like fundamental assertions for distributed system is that they're constantly interreliant. So that means you're often going to require, sort of real-time deadlines for various different sort of yields from various different endpoints, and that means that you have a lot more like reliance on constant traffic, and a lot more reliance on being able to guarantee real-time deadlines between.
So you're saying maybe in the distributed computing world we deal with some kind of guarantees that networking doesn't give.
Yes.
Networking tries to also give you guarantees. It tries to give you reliable communication, can even route messages faster if you have higher priority. Maybe there are more guarantees or different kinds of guarantees to be given at distributed computing. Okay? Yes.
It seems like networking to me is concerned with like how machines communicate, and we're not really concerned with how. We just assume that they can communicate.
Yes. And so what is communicating in our world? We've already answered the question before.
Well, it's just a high level abstraction. Like we say we send this, and then we assume that it gets there.
So that's the networking part. We just say it just gets there.
Yeah, exactly.
So what do we do beyond networking? That is application independent. So what are the endpoints in networking? What are the entities that exchange information? Computers. What are the endpoints of communication in distributed computing? Processes. That's where we come in, we merge operating systems and networking, and we deal with process level issues. Okay? And then the processes can have real-time deadlines and so forth. So communication and networking involves machines and use hardware machine addresses. communicate distributed operating systems between processes and indicate routing information among OS processes. Okay, so we have to get involved in OS issues. So that's the difference. And here's it pictorially, the distributed computing sort of merges OS and networking. You can think of networking also as being related to OS, but we'll just adding some layers in the interrupt management. But here I've shown them as two different stacks. Okay. So can you imagine distributed systems themselves being layered? You can imagine. And how many of you have actually implemented a distributed program? So what abstraction did you use? What did you use?
I did fairly low, just looking at sockets between.
You use sockets. Anybody used something other than sockets?
Emails?
You know, it's very interesting. So email you think of as an abstraction or as an application? So there was a time when I was building the word procedure calls, this is before the web, and I wanted to make sure that there was always an infrastructure I could use underlying that is working. So I said, why don't I send a method call as an email message to another machine? That machine will take that parameters and send it to a process, and that was my transport mechanism. That was my brilliant idea, and I think somebody actually implemented it. Sorry?
Yeah, it's actually used some of the early civilization games support multiplayer for email.
Over email?
Yes.
So there you go. There you go. It was guaranteed to be there, and nobody's going to block that traffic. Because email is something that's expected. So it's not too bad if the frequency of communication is not that high. That's when thread communication versus process communication becomes. So let me just tell you a story. Since you were so quite interested in this thread versus process. So when I was a grad student, we had this claim that distributed computing, parallel computing doesn't scale. Distributed computing scales. So we'll have fast algorithms working distributed. So we built a distributed operating system. And now we wanted to show that we could run things faster in distributed computing. Well, we couldn't find an application that would run faster as a distributed program, except for a checkers program. And I was responsible for making it distributed. And the checkers program was so slow, that the communication across the network was not an issue. Because we built the world's most flexible distributed operating system and the world's slowest distributed operating system. And whenever the DARPA came for demos, I was the most in demand because I had a distributed checkers program. So this whole thing that you can just fasten communication, competition by doing distributed computing, we found in the hard way that it didn't really work that well. Now, people tend to have much more efficient distributed communication nowadays, but it's still not as fast as communicating on a bus. So yes, in theory they're the same thing, but in practice you just have a different set of applications that work well in distributed case. Distribution is more about making resources available, and not so much about making fast operations. Okay. So email is an abstraction over sockets. Anybody, any other abstractions you might have heard of or used in distributed computing? Okay, so you guys have a lot to learn. So in sockets, were you communicating bytes or what were you communicating? Objects or bytes or both? How many of you communicated bytes? How many of you communicated objects? Also, you couldn't tell. You were using Java.
Well, I mean, objects are bytes when they're
I mean, yeah,
serialized
everything has to be
down.
more
So I should say arbitrary objects.
I think he said in that sense, it has to be more collect,
So the bytes is a data structure independent thing. Okay? So everything entrusted in bytes. So there's a whole notion of taking some data structure that you have and converting it into bytes. And those of you who did 431 networking course, you were essentially doing this, right? You were actually translating an email message into bytes. You were serializing it and you were deserializing it. And you can imagine not doing it just for email, but doing it for arbitrary objects. And that's when you get object communication. Okay, so you can have blocking. Now the word blocking, non-blocking, not blocking, make some intuitive sense to you guys. Okay. Read is blocking, write is not blocking. Okay. So sockets, do you think of that as blocking communication or non-blocking communication?
Not blocking, it's just type, you can just send data either way,
And you don't block until.
That's really like application level design, whether you're gonna make, if you're like using this, because the socket's just the medium, you can send on either end, and it's gonna come out. You just have to.
Okay, but does the program block at all by using socket communication?
It can. Yeah, like you can make it block.
If you saturate the link going outbound, you're going to end up blocking. Like if you have 100 megabit per second link and you're trying to push a gigabit per second, that's not going to work. The program's going to block when it tries to send the stuff to the socket.
Okay, it's going to block on what? When will it unblock?
It'll block once that's all the data has been sent out. So in that specific example, after 10 seconds.
So you might block till you block until you get a system block. So blocking, sockets are blocking. There's something called NIO where you don't block. Okay, you say, I don't want to wait till the buffer is clear. Just let me go. Okay? And I'll just trust it will happen. And the advantages, not blocking. Okay, there's more concurrency. So there's blocking communication, there's non-blocking communication, there's object communication, there's pure byte communication. Remote procedure call, what might that be? A lot of you guys like 401. A lot of you guys like object-oriented programming. Can you relate remote procedure call to object-oriented programming perhaps? They don't have to be related, but in Java they are. Yeah.
Because maybe if you have an object stream, you could say, you could send an object and then be like, call this method on this object communicator.
So you're saying, one thing is to go and send an object across. The other thing is that when some data go to another computer, a method is called. Essentially what you're doing is allowing an object on one computer to call a method on an object on another. Okay? That's the mode method. Okay? So you can go and put these things in layers. So there's network byte communication. Okay? There's blocking byte communication, which is sockets. There's blocking stream object communication, so you're sending arbitrary objects. And then remote procedure call. Remote procedure call involves passing parameters. Parameters can be objects. Okay? So that's a layer above the objects. Okay, so now you see that the layering that existed in the compiler world, even in the software engineering world, we talk about layers. Layers exist even in distributed computing. Okay? And you can have non-blocking communication. Okay, NIO. And today NIO is the rage. Okay, because it allows for faster service. And sockets is sort of the only way. Okay. So there's layering here. And now that we understand some of these components, we can go and put some adjectives next to each of these areas. Okay. So we can imagine learning what the design, how the Java NIO abstraction. So we're going to, our implementation will be using Java. That doesn't mean that our concepts are Java based, okay? But we'll be just using the Java APIs. If I'm going to help you program and debug programs, I don't want to deal with C. So Java is a much more tractable language, okay? And it's got some really nice abstractions. Okay, so NIO is the latest, greatest abstraction in Java. So a lot of you were told that this is a practical course. This is practical for many reasons. You will learn about NIO, for instance. Okay, and NIO abstraction design is not so. It's pretty simple. How to use NIO is pretty complex, as I discovered the last 2 times that I taught variations of this course. Okay, you'll also learn the Java's remote procedure call, which is called RMI. Also, I have implemented my own RMI for reasons I'll talk about earlier. Procedure calls, so you learn about that too. So you learn 2 different ways of doing things. It's just you have Python and Java, RMI and gypsy system. What do you think is going to be easier to master? The lower level layer or the higher level layer? Based on your experience with non-distributed computing. Was assembly language harder or was Java harder? Assembly was harder?
Just a little bit.
Anybody think Java was harder? No, the course. I don't mean the same program written in assembly or Java.
Okay.
I'm saying the course, which was harder. What was hard about Java? 401 was not that easy a course, was it? Few of you who took my version of it. So what's difficult, what is easy about assembly? The abstraction is pretty simple, right?
Yep.
It's just, how much do you have to learn about that? How to use it is the hard part. How many rules did you have to learn in Java? Plus all the design. So that's what happens. Okay? That when you have lower level abstractions, it's easy, and this has been a real design issue in systems. You build something skinny and easy to understand that requires a lot of code by each person, or you build something that requires a lot of learning. You build a fancy remote control that no one knows how to operate, or do you just require the person to walk over each time and make it work? So I used to think that, RMI will be so easy to use by students, but I found that students have almost more trouble using RMI than NIO. Okay? Not quite. NIO is harder. Okay. Now I said, I built my own RMI system, not because I thought Java's RMI was bad, but because I wanted to give you guys a way to do some implementation also. Okay? So I built my own system so that we can experiment with it, we can change it, and so you will learn how to actually implement some aspects of RPC, not the entire RPC. We look at the whole design of, so NIO and RPC are two ways for two processes to communicate with each other. There are many more ways. Okay? And these ways differ in different ways. And in some cases, they just take concurrent abstractions, make them distributed. In some cases, they invent new abstractions. So there's a whole variety there. So we look at that in some depth. Okay, so those of you who liked history and Japanese and liked some of the theoretical aspects of seeing the history of things progress, this will be sort of the historical description of the progress that was made. Okay, and we will look at some really fundamental algorithms that have to do with consensus. So, consensus is something we use in English. And for distributed program processes to achieve consensus, you're really saying they should agree on something. It turns out that's a really tough problem, given that processes get failed. And so we will look at some really important algorithms, which are also practical. And so that's the menu. Okay. We look at NIO, we look at RMI, we look at implementation aspects of RMI. And we will look at consensus algorithms. We're not going to look at data pipelines. Somebody was interested in data mining pipelines. So I said one person will be disappointed, but the rest of you, this is going to challenge you, but it should also be okay. So so just as just to sort of reiterate what I've said already. So you've done some numeric computing perhaps before, you've done some functional programming before, and some of you got excited by numeric computation, some of you got excited by object-oriented programming. My generation learned functional programming, so that's why I've got functional there. Here you will learn, in abstraction use, you will learn how to use NIO, RMI, and also an abstraction that I've created for those distributed algorithms, which is replicated objects that you can converge to create a consensus. You'll see what this means later. Okay, I'm giving you a preview, so if you're not understanding quite what I'm saying, that's good because you have something to learn. Okay, so I'm just giving you a little bit of an idea of what to expect. Okay. You will, just as you have, compilers and interpreters, we will learn how to implement serialization in RPC. Serialization will be extra credit, and RPC will be required. Okay? So you'll implement some aspect of RPC, okay, which is again going to be a very good practical skill. So just as you have models of computation and algorithms associated with them, such as sorting, we will learn about distributed models and algorithms, fault-tolerant consensus. Okay, so that's. I'm just reiterating in a different way what I said earlier. So this will be a very practical course. Okay, this is all implementation-based, assignment-based. Okay, so I've designed a set of assignments, and my goal is to make sure that you can do these assignments. That's my goal. There's a lot I can cover, but after trying trying this course a few times, these are the set of assignments that I've come up with. I'll talk about those. And again, to sort of relate this to what you learn in non-distributed programming, so in 401, those of you who've taken 401 from me, you know that you do one big project over the course of the semester. And those of you who've done it recently, we've been using the Monty Python's Holy Grail application. So one of the applications, and before that I used to change the project each semester, each year. Okay, so every summer I had to dream up a new project. And then I started focusing more on auto-grading and other things that cost projects constant. So one of the projects was a Halloween simulation, where a person could visit from house to house, could go and take candies, could return candies, could do and undo. There's a lot of interesting things you could do here. Okay, I won't get into the details of the application, but this was a particularly nice simulation was created by a student called Bo, and we're going to take his Halloween simulation and make it distributed. We're going to treat that as a black box, okay, and make it distributed in various ways. Okay, so that will, separate out the non-distributed computing aspects from the distributed computing aspects. You'll still have an interesting application, but you wouldn't have had to implement the non-distributed aspects of the application. Okay. I should really end at this point. So I have actually 50 slides here in the introductory part. So we'll probably take one more class. I haven't quite set up my web page. Okay. I need the weekend. I was supposed to arrive 14 hours before I did. Thanks to weather, I got delayed, so those 14 hours it cost me some of this work. But hopefully I'll get that done soon. So lots of you, I think all of you are, or from what I remember, only one person hadn't signed up with Piazza when I sent out the Piazza invitation. So please sign up with Piazza if you haven't. I'll be using them for announcements, so I'll provide you material to look at. And I haven't quite answered your questions about research papers, but we'll get to that next time. Okay, so we saw last time that distributed systems sort of builds on two sets of layers, operating systems and networking. Okay, so as you've seen, both the prerequisites are either OS or networking. Asking you to have both prerequisites is too much. So, one is all we ask, and this is not my requirement. This is something I inherited from when the course was taught before I taught it. Okay, and now those of you who've done networking, have you learned enough to create an arbitrary distributed application? Is there any distributed application you can't create using what you've learned in networking? That is creatable. I mean, that's, a Turing machine can implement. You've learned to send bits from one computer to another computer. You've got a Turing complete programming language. What more do you need? Right? So, anybody want to say that it's not a complete system in some way? Okay, assuming it is a complete system, what do you think distributed computing is adding then? I mean, what am I going to teach here? Or what needs to be, yeah.
Probably some abstractions.
So, you know, you can code anything in a Turing machine. None of us programs using Turing machines, right? We can program anything that in an assembly language or machine language, but we don't do so. So we need abstractions, okay? And abstractions is something you've learned in your various courses, Java, operating systems, and abstractions. And what else might you want to know? So abstraction makes it a software engineering problem. So some of you said that, look, one of our favorite courses was software engineering. Okay, so this and software engineering is interesting for two reasons. A, you build a practical application, so that's great. Plus, you use the right methods and abstractions, so that's that's good. So it's a software engineering course, and it's an engineering course. And where does theory come into this picture? So just because you can build it, I mean, theoretically, does it mean you're able to build it? What do you learn in algorithms? You learn, on your own, you might not have come up with quicksort and heap sort. Okay, so you're taught certain algorithms that are hard to come up with on your own. So we'll also learn how to use these abstractions. Okay, so it's not just abstraction design, but abstraction use in terms of algorithms. And also we look at abstraction, since a lot of you are interested in systems, and often the way you really understand an abstraction is to see its implementation. We also see implementation, right? So we're going to add stuff over both OS and networking. Okay. Now, there's many ways to teach this course, and I mentioned last time that we're going to take a very implementation-based approach. Okay, which means it's going to be what you're going to learn is going to be governed by the assignments you do. So my goal is to basically give you, I can't teach you everything. Okay, I can teach you only a small set of things that are part of distributed computing, and the goal is that you can do those assignments. Okay, and hopefully the choice of assignments is such that you will learn the more basic fundamental concepts. Okay, but you can see that that's quite a challenging task, given that people haven't tried to cover the same space that I'm trying to cover here. What people have covered has typically required you to be a graduate student. So I'm trying to cover something that would be meaningful to an undergraduate student and doable by an undergraduate student. So we will look at abstraction design, abstraction implementation, abstraction comparison, and implementation, and some algorithms too. Okay, so when we look at abstraction design and use, it becomes like a 110 and 401 course. It's how to program. When we look at abstraction comparison, it becomes like a comparative programming language course. Anyone taken a comparative programming language course here? Anybody taken the programming language course we offer here?
Hasn't been offered in a while.
Hasn't been offered in a while? It's going to be offered this. Diane is teaching it this semester, right? Yes. So what's typically done is, you compare multiple programming language designs. Okay, you compare logic programming, functional programming, object-oriented programming. When I was your age, Pascal, like in conventional programming, was what was traditional, and object-oriented programming was this new and novel form of programming. So we're going to, and abstraction implementation makes it like a compiler course. Okay, and the algorithm data structure makes it like the algorithm and data structure course. So we are trying to make this course multiple things, and it's going to be tricky. Okay, but if we can do it reasonably, we can't do it perfectly. Okay, but if we can do it reasonably well, we'll learn a lot. Okay. So let's look at the assignments. Okay, so given that there's this big space to cover, to come up with a set of assignments that are connected to each other in some way is challenging. Okay, and because it's challenging, again, we won't get it quite right. Okay, but we might get it right enough. Okay, so let's go and see what it means to get right enough in this course. So this is about distributed computing. We want to focus on the distributed aspects of computing. We don't want to focus on what you already know. but it'll be nice to have an application that makes intuitive sense, is appealing to some degree, and often appealing means it's got to have a user interface and do something. It shouldn't just be, some invented application that has no meaning on its own. So we're going to start with this Halloween simulation that I talked about last time. And the idea is that there is a person going from house to house taking candy, and they can take candy if they approach the house. And in this application, you can take candy, you can return candy. If you take too much candy, interesting things happen to you, and you should try this out. The student who built this was quite creative. And you can undo what you did, you can redo. So it seems interesting in its own right, and from a distributed computing point of view, it's particularly interesting because it brings out certain conflicts that can occur in distributed computing if you don't do things right. Okay. So this is a single user application. Again, like I said, you can move the person around, you can approach a particular path, you can approach a particular house and take candy and return candy. So that's simple. What would it mean to make this distributed, by the way? There's many ways to do so. And the one I've got here may not be that intuitive, so let's discuss that. So you can run it all on one computer, okay? And one user is running it. When you make it distributed,
one server which manages all the houses, and you have multiple clients connect to it, each of which will represent a single person going around anything.
so that's one way to do it. You have the houses that are user independent in the server, and each client would represent one user. You're thinking of a game, okay? And each user would have their own avatar, and they could move them around, okay? To do that would be tricky here because the underlying application would have to be changed in significant ways to allow multiple users to be around. So can you think of a simpler way to distribute this that has only one user in the simulation but is distributed? So there are multiple clients, the program is running on multiple computers, but there's only one user moving around. So
You just have one server, one client in that case.
no, you want multiple clients, right? Otherwise it's becoming too simple.
Every client will just move the same person, move the same user.
So every client moves the same person. Okay, that's what's going to happen. So you're basically replicating this. Okay, and so we don't want to deal too much with the underlying application. Okay? So there's only one person moving around, but there are multiple clients, and you can feed input. So they can be real users feeding input to their clients, and these inputs get all collected together into one stream, and I can move the client to a certain distance, and you can undo it. Somebody else can redo that. Okay, so you have basically the same UI, but just multiple controls. Okay. Okay, so that's your simulation. Now, the good news is that this is already built, so you don't have to build it. But the bad news is that you've got to interface with somebody else's code. And that is potentially scary. Right? But I'm going to argue it's not so scary. And the reason is that this was a COM 401 project. Right? COM 401 is supposed to teach you how to code well. And if it's been coded well, you only need to know about things that you need to know, and not superfluous details. And that's exactly true. Okay, so interfacing with this, once you've got the code downloaded through Git, running it and interfacing with it is the most trivial part. Okay, so that's the good news. Okay. So again, Bo Anderson was a student who did this project about a decade ago. Okay, so we've got an existing non-distributed simulation. We want to make it distributed in the way I talked about just now. And we're going to use Java NIO. Okay, and NIO stands for non-blocking IO. Anybody want to guess? Anybody heard of Java NIO before? Okay, so we've got to use our imagination. What do you think non-blocking IO means in the context of distributed computing? Just, who knows what that really means? There's many different answers possible. Let's just try to see, use our intuition, use our knowledge. So, blocking. Yeah.
Blocking is blocking the execution of whatever process or the program is running on. So it's either if you're communicating with another machine and you have a non-blocking program, then as soon as you send a message or UIO to the other computer, then the program will continue executing and it won't be held up waiting for a response.
So the interesting part here is that a process or a thread can block or not block, right, in general. So, and what you're saying is that when you're communicating, you don't block after communicating. So you're communicating by executing some set of operations. And those operations don't block your thread, okay, or your process if that's the only thread there. That's what you're saying? So to really understand what non-blocking I/O is, we've got to understand what kind of operations we need to communicate among computers, and what blocking really means. And so let's try to understand a little more deeply what blocking means. Forget distributed computing. Just good old 101 programming or CS1 programming. In CS1 programming, have you seen any blocking operation? That operation that blocks the thread? Yeah. I/O. So what kind of I/O? When I do a print, when I do a print, do I block?
No, specifically when you do input.
So when you do a read,
Yeah.
you block. When you do a print, you don't think we block.
It's functional, but the print isn't waiting for any input outside of the program.
Okay. So print is not waiting, okay, but read is waiting. So when it's blocking, if you ever go and debug and you do single stepping, you'll see you can't just step further. It's just blocked. Okay. It so happens that print is inherently non-blocking, or the implementations of print that you've seen have been designed to be non-blocking.
Anything can be implemented to be, a lot of things can be implemented to be blocking, but there's no real need to,
There's no real need to.
So if you have like some standard out, right, and you write something to this handle, you can maybe wait for the terminal to display it, but that it's not at all necessary, to have it blocked. So you could potentially implement it this way.
So you're saying that it does, maybe there is, so we saw earlier that sending a message could be blocking, right?
Right.
So what does that mean? We don't quite know. But you've just said that, look, when you print to the terminal, you could potentially wait until the terminal has displayed it, right? But you're saying it makes no sense to block you.
Well, I mean, there is potential where, like, okay, if you have, in like Unix terms, right, you have a handle or a descriptor of some kind that you write your standard output to. So that might take a non-trivial amount of time to write this. But in much the same way that it might, if we have some non-blocking I/O, if we have some, messaging system to, like, actually read or copy, from that buffer to memory, to your heap space, whatever that message is, even in non-blocking I/O does take some non-zero amount of time. But we don't consider that to make that I/O blocking.
So you're saying that, okay, it's a question of time, and it's, if the time is small, it doesn't make even sense to distinguish between blocking and non-blocking. That's kind of what you're saying?
No, what I was saying is that there's, with every, when we say non-blocking I/O, we mean that we're not, that we might be waiting on the actual mechanics of the I/O, the read or the write, but we're not waiting for that to become available and blocking the execution while it's becoming available to us.
In non-blocking.
Yeah, non-blocking, we don't wait for it to become available.
So we don't wait for some resource that we need to do the operation to become available.
Yeah.
And in blocking we do. So when you do a write, what's the danger? Do we need some resource there? Is some resource needed to make the operation really work? Is some scarce resource that may not be available? Is there a problem that there may be some resource that is not available to do the operation?
Yeah, whatever descriptor you're writing to or whatever handle.
The descriptor will be available. The descriptor is just an ID. It's just a name. But the descriptor is going to point to something, right? So think of. So you guys who did OS, how many of you done OS? Okay, good. So just think of forget bitmap displays. Just look at console and interrupts. You guys did interrupts at all? No, you did interrupts? So can you relate output to interrupts? Are interrupts involved in output?
Yes.
In what way?
It's like a protected system call. Like we're not, the user program's not on the right, so we have to do interrupts to the system to protect that resource, protect our output resource, and then we can do the right.
Okay, so that's interesting. Interrupts execute in what's called the kernel. Okay? And the kernel executes in what's called the hardware kernel mode. Okay, so the hardware provides a kernel mode, and what's the opposite of a kernel mode? User mode. And kernel mode is more privileged. Okay, so user mode is less privileged. So if I'm a process, I execute in user mode, I can't munge around with kernel data structures, which is good because they are shared data structures between all users. So interrupts execute in kernel mode. So you're saying whenever you do a write, who knows whether you should be allowed to write or not? Who knows, whether the resource is available or not? So we should execute in kernel mode, and interrupts definitely execute in kernel mode. But not everything that executes in kernel mode is an interrupt. Okay? Yeah. No. Okay. Yeah.
And, even if we do make a system call, to write, there's not. We could do if we do a system call that involves like looking at a page table or something, and that would require some kind of shared resource. But that might have something there. But if we're just doing a context switch and making a system call, then to write to standard PAL, there's no we can run that kernel mode code in any thread and continue execution. So it requires a context switch. But I don't think it's too different than calling any other library.
So what you're saying is
In
that
case, at least.
you agree with him that we'll do a kernel switch.
Right.
Okay? A kernel switch means switch to the kernel mode, execute in the privileged mode, but you don't think there's an interrupt involved in output. In input, is there interrupt involved? When you type something on the keyboard, that's a device.
Yeah.
The device will tell you, hey, I've got something for you. Okay? So an interrupt occurs and you consume it.
Anytime we do a read or a write, we're having to interrupt.
So why are we having to interrupt and write? I mean, I haven't, I think he's implying that we don't.
No, I think I'm saying even if we do have to interrupt, right? That interrupt is not being used because if we're talking about like blocking versus non-blocking I/O, I think the fundamental distinction there is that there is a resource that needs to be waited on, or there's a resource that could be contested, or there could be, especially in the case of input, the input could be not available. One of these cases, but even if we do use an interrupt, in this case, the interrupt that we use for writing out the console is very, very similar to any other system call. It might have a little bit more meaning, or might be a little bit heavier weight than a typical system call, perhaps. But we're still not it's still not blocking I/O because there aren't these resource convention issues.
Okay. So I want a simpler answer. Why is an interrupt? Let's forget about contention. Let's forget about blocking versus non-blocking. I'm trying to lead you to what I think is the answer. Just tell me why is there an interrupt involved in output or not, and why? Why is there? And by the way, an interrupt is not a system call. So a system call is what happens when you go from a thread to the system kernel. You say read, write. That's a system call. Okay? From user space, you're going into kernel space. An interrupt involves multiple devices: keyboard, screen, computer communication network. Okay, talking to the CPU. Okay, so we've convinced ourselves that when we are doing input, the way the keyboard tells the kernel, the CPU, that there's something available is by it interrupting the kernel. Okay, and it's connected to a bus. Okay, you guys have all done 411, I guess. Okay, so there's a bus. CPU is connected via a bus to these devices. It goes and writes data to what are called device registers. Okay, they behave like memory, except that they are actually part of the device. The device goes and says, I've got some data. It writes it on the device register, and then it tells the CPU, hey, I've got something interesting. And the CPU then goes through the bus and accesses the device registers. So we know for input the data is coming in. So we have device registers, and we need to be told the new data are in. So I still haven't got, forget about non-blocking, blocking. Just tell me why we need interrupts in output.
If maybe your writing involves using a device, then we have to know when the device is finished writing, and interrupt can be used to transfer control back to the device.
So we need to know, the device registers. So those of you who've done operating systems have heard of the bounded buffer. Okay. And so at some point, those of you who've done operating systems will feel good. We know this, and the other guys don't, and it'll be the reverse too. Okay, you guys have not sent bits across the network. So the guys who've done networking are going to be in a better spot, actually, for that reason. But you guys who've done operating systems know some of this stuff, and that's going to be important. Okay, so we know that there's a notion of a producer and a consumer in a bounded buffer. Okay, so what's a bounded buffer? It's just a list. Okay, it's a list that's accessed by not one thread but multiple threads. Okay, and some threads add things to the list, some threads remove things from the list. Okay, since these are independent threads, they can go at different rates. So why is blocking relevant in a bounded buffer? Yeah.
Sorry, so it's full.
If it's full, if you're a producer and it's full, you can just give an error message saying, sorry, it's full, operation not allowed, or you can block. And you may also block when it's empty. If you're a consumer and it's empty, you block till it's not empty. Okay, let's go back to the device registers. So we have not two threads, but we have a CPU and a device running in parallel. They can go at different rates. CPU can often produce data at a far greater rate than the device can consume. So we've got to have a bounded buffer, which are the device registers, and typically that's just a buffer of size 1 in some of the primitive implementations. So the CPU should not go and write there till it knows that the previous operation has finished. Okay, so there's a blocking issue. There's a synchronization issue there. And now the question is, should you block the user till you can actually do the operation, or shouldn't you? And if you don't block, you've got to go and fill up the buffers. Buffers are costly. Okay, so whether you're sending data across the network or to a device, there's an issue of whether the buffers are available to complete the operation or not. Okay, and maybe you're not writing as much data. Okay, so we don't really need to think about blocking, but whereas to the console, but whereas when you're sending data across the network, you can be sending huge amounts of data, so maybe blocking is more important. But conceptually, in both cases, there is an issue of whether you block or not. Okay, and so in any operation, you can talk of the operation completion time, whatever that means. You can say this is when the operation completes. The operation completes because the data have gone across the network, have gone into the device register, have been shown in the screen. At some point, you think it's complete, and the question is whether you block till it's complete, or you block till a little earlier time, or you don't block at all. Okay.
just within the Unix space, right, doesn't the, isn't there some sort of thing that manages these buffers, at least for like at least for the terminal output, for example? And my thought is like here it seems kind of like the kernel when we provides a sort of non-blocking I/O library or some kind of abstraction there that we then would use. I mean, even if we have a device buffer of some size, we can still issue kernel system calls to write more than that. And the kernel uses some internal structure to, might have a larger buffer than might be implemented in the actual relation, in the actual connection.
So you know, the kernel can have a very large buffer space, okay? But there's actually, you guys haven't used it, you have never done this before, but there's actually the kernel will start giving you error messages when the buffers overflow.
Oh, okay, that we're
Okay.
doing. Now I understand.
It'll actually tell you that, sorry, even if you type too fast and it can't consume it, it'll start giving you error messages saying, you know, my buffers are full. Okay, so there are buffers, and so this is important. Okay, so when you guys are studying networking, you didn't go into buffering and kernels and things like that. You just said, okay, this is how we send data. You guys who've done operating system don't know how to send data, but you at least understand some of this aspect, and we need to sort of understand both in this course. Okay, so non-blocking I/O is a general concept. Communication among processes is considered a particular form of I/O. So Java NIO will tell us how to use non-blocking I/O to communicate among processes. Okay, and if you don't quite understand what we've been talking about, that's okay. That means you have a lot to learn. I'm just giving you an overview at this point. Okay. Questions? Okay, so blocking means that a thread is not allowed to go to the next step. Okay, and in the context of communication, the reason why you would block is because you don't have, for instance, buffers to write the data. Okay, when you're writing, or you might block because you're trying to read and there are no data available for reading. In either case, blocking makes sense, and whether you actually whether you actually block or not depends on whether the thread that's trying to write wants to know about errors or not. The thread can say, okay, I'm sending the data here. If you can send it, send it. If you don't send it, don't bother me. I just don't want to stop. Okay, so that's one philosophy, and there are many other philosophies. Okay, questions? Yeah.
So, with non-blocking I/O, does that mean like you as a programmer are responsible for a situation in which like, you wouldn't be able to send or receive data because you have an empty buffer on the other end?
So with non-blocking I/O, there is a way. We need a way to tell the process that didn't block, hey, something went wrong, so that it can recover.
Right. So, would it be like some sort of Boolean return or functions, or you would
Something like that. So we'll see the details, but you can see now some of the issues that are faced in this. Okay. So some kind of Boolean or some kind of. So let me ask you. Think 401. How might I be notified later about some operation, some status of an operation? Okay. Yeah.
Just a flag instead of Boolean, or just let's see, we just use an integer 1 or 0.
So there's a flag that you keep polling, that you say, okay, did it go through? Every now and then you have a little loop. Now, those of you who don't OS, how good is polling?
Yeah.
Today is the world of web programming. And web programming, sometimes you can't avoid polling. So students who do web programming, they just use polling with abandon. Whereas, when I was growing up, we were told polling is really, really bad. Okay, so if you're not polling, how might you get to know about something that the system has done? Think, yeah.
There's an exception that's there.
An exception could be thrown, but that's, that means you're waiting for it, right? You made a call and you got an exception. Hey, you didn't wait. So you're thinking 401, that's good. What other mechanisms have you learned in 401? Some design pattern? The model view controller pattern builds on observer pattern. Okay? You might get a callback. The term in OS, you guys have heard of the term callback? Callback is basically an observer pattern. Okay? You're being notified later. So that's the kind of mechanisms you have to tell you that the operation didn't complete. Okay, so you typically what happens is that you get a callback saying, hey, you want to do a write? I can do a write right now. So you don't just write and then hope things go well. You get a callback saying, if you have something to write, now's the time. Okay? Questions? Okay. And now I use the word synchronous. So I've used blocking, non-blocking, and I'm going to use synchronous and asynchronous. And anybody know technically, we'll use our intuition to figure out the difference between blocking and synchronous. But anybody know technically the difference between synchronous and blocking? Okay, so let's use, yeah.
So I guess blocking in the sense we're waiting for, you mentioned we were waiting for an interrupt or some kind of indication that we were ready. Synchronous, we're going to operate in lockstep. We're only going to operate once the other process has been, it's completed. We're not necessarily waiting for a message, we're waiting for the other process to
Okay, so that's interesting. So blocking means, did the operation complete or not? Synchronous seems to involve a second party. And the two parties need to be synchronized. Right? So think of your car waiting in traffic on a stoplight. And now think of a car rally where you're waiting for the previous person to come and a relay race kind of thing, a car relay. They have those, right? Sure. They still do? They had it in my times, where you're waiting for the previous car to come and then you take off. So which is synchronous and which is blocking? Just blocking?
Synchronous should be the relay.
Synchronous means there's, a synchronized swimming, a synchronized carding, where there's another party and you're depending on it to do your task. And blocking is, I would love for the task to be done in 0 time, but it just can't be done, so I'll just wait for it to be done. Synchronous implies blocking. Blocking doesn't imply synchronous. Okay, to waiting for the other car to come, you have to block. Okay, but that's a logical step, whereas blocking is sort of accidental and physical step. Okay, so what might RMI mean? Remote method invocation. Okay, and that's an example of a more general concept that was built in the context of non-object oriented languages. So method is a term you use when you're invoking operations on objects. Okay, but procedures is a more general term. So it's an example of RPC. Okay. So we understand that Java has an RPC mechanisms for methods, which is called RMI. Now so this assignment will involve understanding RMI. The goals of RMI are to make local method invocation similar to remote method invocation. So if the goals are really met, this is going to be simple. Okay, but it turns out nothing is simple in life, and so you will learn here too. And underneath, RMI uses sockets. Okay, it doesn't use NIO; it uses sockets. Okay, and so sockets are blocking. So RMI would be blocking. Plus RMI is synchronous. So what might synchronous mean in the context of a method call? Remote method call.
wait for the method to finish and return it.
So the calling object on one computer waits for the method to be executed on the other computer completely and then unblocks it. Okay? And it's much easier to program using synchronous programming rather than asynchronous programming. Okay? Now I've got the word serialization here. And how many of you know, how many of you know what serialization is? Okay. So those of you who don't know what serialization is, can you try to guess what it might mean? So something that's being linearized somehow. Okay. So imagine a tree data structure being converted into a linear form. That's the word, what serialization means. And why might that be done? Yeah.
Well, just like an example would be JavaScript serialized object notation for communicating information about a tree-like structure like an object, but putting it, if you need to put it in buffers, then it has to be organized in a linear way.
So if you're sending bytes, that's what you're doing in networking, right? So there's an impedance mismatch. Okay, what you're sending are data structures in memory, which could be graphs, trees, whatever. Okay, with pointers, and what you're sending on the stream is a linear sequence. So somehow you have to go and convert this structure into a linear sequence and then uncode it and convert it back into, so that's called serialization. And deserialization is converting it back into the data structure that you're sending. Okay, because you really want to be able to send objects. You don't want to send, some of the early RPC mechanisms just sent primitive values, ints and reals and bytes. For that, even that is tricky because an int might be represented in a different way on one computer and a different way on another computer. There's the big endian and small endian mechanism. So you have to go and have a network representation that's standard and convert between these representations. And when you start going into complex data structures, that's even a bigger challenge. Okay? So if you're going to do remote method invocation and you're going to make remote method invocation similar to local method invocation, you want to be able to send arbitrary arguments to these methods and get arbitrary results back from these methods. That means you should be able to send be able to serialize and deserialize arbitrary data structures. Okay? RMI hides that serialization from you. It's just there. Okay? And the reason why I mention it later is because one of the assignments makes you do your own serialization. Okay, now those of you who did the networking course, can you relate what you did to serialization? You guys built a mail server, right? So can you see that as a form of that? Can you argue that was serialization?
The text, like in the email, is just serialized into a byte string that you send.
So there was a structured object on your computer. Email message is structured. You linearized it, and you undid that. That was a particular data structure. Now the task is to take arbitrary Java objects and convert them into linear form, and including graphs, which is very tricky. Okay, so that's a challenge there. Okay, this is challenging enough that I'm making that an extra credit assignment. Okay. Questions? Not this assignment, but the one that will involve serialization. Okay. Now, invoking methods synchronously seems like a no-brainer because local methods are done synchronously. But has anybody used, or do anybody know of some mechanism that does methods asynchronously? Yeah.
Kind of like in Node.js, the event loop.
So Node.js allows you to.
Web API calls and non-blocking, so execution of the server.
Okay. So in general, in web programming, we need, if you want method invocation, you want asynchronous. And Google's got APIs to have a generic remote method invocation that's asynchronous. Okay. So I built a system called Gypsy for generalized IPC. IPC stands for inter-process communication. That has asynchronous method invocation. Okay. And it's non-blocking, and it uses Java object serialization, but it builds on the NIO layer. Okay. So rather than on the socket layer, it builds on the NIO layer. So your assignment 3 is going to provide a branching point for different aspects of the course, compiler aspect, the language aspect, and so forth. So one of the things you'll do in assignment 3, which will be the most trivial part actually, is to write yet another way, implement yet another way to communicate messages between clients, and this will involve using Gypsy RPC, okay, the asynchronous method, asynchronously. Okay, so that will be interesting. because it's asynchronous. But what's particularly interesting now is that you've got three different ways to communicate among the clients. You can use NIO, you can use RMI, and you can use Gypsy. Okay? And that brings us to some more adjectives and some more terms. So let's look at the various terms here. Consensus. What might consensus mean? Anybody heard of distributed consensus before? So let's use an intuition. What might distributed consensus mean?
All parts of the system have to agree on some value.
So imagine, assignment. Okay, when you're all on one computer, we can all agree what's in memory. Imagine now a replicated object, like our simulation. Imagine a replicated assignment. And all parties have to agree that this particular variable has this value. Okay. That's consensus. Fault-tolerant consensus? What kind of faults are we talking about? Yeah.
You have kind of like the element of game theory. You have parties acting in the network that are trying to sabotage it or use it for their own advantage and trying to spoof whatever data it might be you're trying to validate. So you need some way of ensuring against that.
Okay, so where did you study this stuff?
I'm just kind of interested in cryptocurrency.
So have you heard of
like that.
Byzantine failures?
Yeah, kind of like the theory.
Okay, so that's, you're into the conspiracy theory kind of stuff, that some agents might just be malicious. What's even a simpler problem?
Then it fails.
Just a computer fails. And do you even know whether a computer failed?
Yeah,
Is it just taking a long time?
Not immediately.
Do you ever know it's failed? The computer failed. How would you know that the computer failed? Given that messages can take an arbitrary amount of time to reach. So you can try to make guesses, okay? But theoretically, you just can't know whether a computer fails, okay? So that becomes an issue. So what we'll do in this assignment is assume no faults. Assume that the data will reach, computers' nodes don't fail, messages always go through, and just build a consensus algorithm from scratch. So that you understand what consensus means at least. Okay. And what are we going to agree on? So I said, some variable has a particular value. What we'll agree on, we have three different ways to communicate. Our Java program can use any of those three ways to communicate with other Java programs. But you can't have one system sending NIO messages and the other one expecting RMI calls. So they all have to agree on what the current communication mechanism is. So we'll allow this to be changed dynamically, but we will make sure that before we change it, we all agree on what the current mechanism is. Okay? So that was my way of creating an interesting problem that requires consensus. Okay? So that's going to be the second part. And again, it's not going to be very hard. Okay? Now, what do you think centralized means in this context?
There's one machine that determines what this value is.
So there is one distinguished machine that other machines rely on, through which consensus is achieved. Okay. So there is non-centralized consensus too, which we'll study later. But this is going to be, just like I said, I'm really simplifying the problem. Okay. But you'll at least understand, and this is not totally unrealistic. Okay. So we'll do this as part 2. Now, here's an interesting thing. We're doing distributed programming, but most of you just have one computer with you, and to have multiple computers is a challenge, and debugging on multiple computers is tricky anyway. So we're going to do most of our debugging on a single computer and a demonstration on a single computer, but it would be nice to run some experiments on distributed computers and to look at infrastructures that will give you distributed computers. Okay? And you guys know about all kinds of services that provide you with cloud servers. Okay? And I've been working with folks at University of Arizona on what's called a cyber infrastructure. It's meant for academic science. And they've got a system called Atmosphere, Cloud Atmosphere, that allows you to go and reserve computers in the cloud. And just to get some practice, just to get an idea of what this particular infrastructure looks like from a user's point of view, at least. Okay. You will run some experiments on this. Okay, so that means you have to create accounts here. They let me create accounts last time. Hopefully they'll still let me do it. Okay, so that will be part 3, where you will run actually distributed experiments involving a real network and compare the performance of these 3 kinds of mechanisms. Okay? The asynchronous RPC, the synchronous RPC, and no RPC, just pure NIO. Okay? And these 3 parts will sort of launch off different aspects of the assignments. So let's go back to the part 1, where you use Gypsy RPC. Now, I told you I built my own RPC system, and why did I do that? Don't I have anything better to do, given that there's RMI? Anybody want to guess why that might be relevant? I did it just for this course. Yeah.
RMI might be very limited to only Java-based, or might not even be commonly used in real world at all, and your system might be more akin to.
Oh, I wish I could go and compete with RMI in the real world. I think it's a system that can compete, but that's one reason why you might want to use RMI. Actually, RMI is used in the real world as long as you're not doing web programming. People are quite happy with that. But I think the reason why I think this is a good competitor is because it's more efficient. It's on top of NIO, and RMI is bound to NIO. But what's the advantage of building something just for? I did it only for teaching. I didn't try to go and change the real world. Why might I do something just for teaching? Have you guys seen any teaching infrastructures before in your OS? How did you guys implement things in the OS, by the way?
Various C programs.
But did you do any kernel programming at all? No.
If you participated in the honors section, you could do some kernel level stuff.
So what did you change? Linux?
Linux module.
Sorry?
Yeah, Linux module would be some external modules.
So you changed the Linux modules?
We didn't. We used the module and we built another module which used some functions.
But you got into Linux. You basically extended Linux. That means Linux is extendable. Okay. So expecting you to write the whole Linux kernel is too much, right? Expecting you to implement completely RPC from scratch is too much. But I can expect you to implement some component of it. That means I need to build a system that is extendable, where you can change various components. So I built the system so that you guys could extend it. Okay, and RMI is not extendable, in at least the same way that, at least based on my knowledge of it. Okay, so what you're going to do is go into Gypsy, okay, and add synchrony to it. So Gypsy by default is asynchronous. Why don't you go and you'll add a module that makes it synchronous? That means you'll have to go and interface with all kinds of components in it that make the rest of the RPC work, which means you'll have gain an understanding of what those components look like. Okay, just as when you added your module had to go and interface with other modules, so you got a better understanding of those modules. Plus, you learned how to go and change your own, implement your own module. Okay, so one of the assignments will be sync RPC, and you'll understand what's involved in implementing synchrony and blocking and synchrony. So not only will you learn how to use synchrony, you'll learn how to implement synchrony, which will involve distributed synchrony. That means you have to go and send distributed messages to make sure that things are synchronized, that one end is coordinated with the other end. Okay. Okay, and you know, it's doable. It's not too hard. Now let's look at another component. Let's look at that centralized, non-fault tolerant consensus algorithm. What we'd like is a non-centralized, fault-tolerant consensus algorithm. Okay, and that algorithm, there exist a bunch of algorithms. Okay. Implementing any of them would require more work than I can expect. from you guys. So what I've done is, and also I want to understand these algorithms myself, I have built an abstraction that has some very important algorithms. Okay, so the set of algorithms that people learn in the graduate operating system, graduate courses, they prove them, they learn them, I just implemented those. Okay? And I don't need you to re-implement them, okay, because they are standard algorithms. So you won't be implementing these algorithms. But I do want you to understand these algorithms. So imagine sorting. Okay, imagine I've implemented quick sort, heap sort, bubble sort, okay, bucket sort, all the various sorts. Okay? And I want you guys to understand sorting and understand the pros and cons of these algorithms and understand how they work. So what you'll do is, and you know that certain algorithms work better in certain conditions. So to understand these algorithms, you have to know the conditions under which an algorithm works better than some other algorithm. So you will go and create conditions favorable to each algorithm and see what the algorithm does under each of these conditions. Okay, so you'll trace them, so you'll just understand algorithms by running them under different conditions. Okay, and I'll tell you exactly what to do. So it's doable, and yet it will be, you will learn. Okay, that's part one. You get an understanding of, so my abstraction can be just configured to implement different algorithms. So this is a configurable one, and you will just learn how to configure it and use the algorithms and see what happens. And when you're talking about fault tolerant, I mean running fault tolerant, introducing faults and seeing what happens with faults, I mean that's quite complex. Okay, so there's a lot of learning involved here. Okay. So change configuration, introduce faults, and understand algorithms behavior. Okay, that's what you're going to do. That's part one. Second thing is to use this abstraction as yet another way to communicate objects, communicate concurrence. Okay, so I've got this abstraction, you'll just run it on an example application. Now you will take your application and interface with this abstraction so that you understand consensus a little bit, even better. Okay. And the last part is recursive, that there's multiple ways to reach consensus. How do you reach consensus on what consensus algorithm you're going to use? Such recursion is always great. So we'll use a particular consensus mechanism to achieve consensus on the other consensus. Okay. So assignment 3 is assignment 5 is it's the last assignment, required assignment, and it's not going to involve heavy programming, but a lot of understanding. Okay. Okay, now I introduced the idea of serializer, and I introduced it to tell you that, look, that's something that's worth learning about. And so assignment 6 will involve writing your own serializer. And that's extra credit. There'll be some quizzes associated with it that are also extra credit. And I'll tell you, I'll talk about how much the credit would be. So this is something you can start on today if you want. The material for it is available, will be available on the web soon, just as soon as I get a chance to update my web page. And this is something you can do throughout the course, whenever you have idle cycles. If you want to do the extra credit part, this is available to do. Okay? Questions so far? The reason to do this is that this will be worth as much as the final exam. It is I think the most complex recursive piece of code I've written. But I'll give you enough hints to do it. It's doable, but it's something that is challenging, but doable also. And students who, the final exam is, in an undergrad course, is not off. You have to come to class. So the students who had got an A before they came to the final exam had the biggest smiles on their face as they came in, wrote their names, and left the room. Okay? So the reason to do this is that you don't have to study for a final exam. You don't have to take it. One student had done the serializer and took the final exam anyway. And he had the worst handwriting of all. And I knew there was no point in grading his exam, but I still did it. So, but that's the incentive. Okay. So, this is challenging, and one student sent me a message saying no textbook, and you're doing something quite different. Should I be worried? And what resources will be available? So let's look at that aspect. Okay. Firstly, I have some practice. So getting any course right takes a long time. Okay. I've taught 401 for a long time. I still haven't got it right. Okay. And who knows how programming should be taught, and who knows how distributed programming should be taught. Okay. But we all try. And so there's always going to be some obstacles, things that can be improved. But I have taught a version of this course to graduate students. Okay, that's how I started off. Okay, so there's some experience there, but at least the serialization assignment came from there. Then last spring I decided to teach 533, and that was a learning experience for me and for them. But we ported the course to undergrads. And I was quite happy with it, and so was most of the students, as far as I could tell. Except that in the first 2 weeks, there was a big, I think 1/3 of the class dropped. Okay. And, my principle always has been that let's make the students work hard in the first 2 weeks of class when nobody else is giving them assignments. So that's my goal. The last 2 weeks, no final exam to be studied for, and maybe not even an assignment to do. So I always like to sort of, make it easy for you in the end. And in 401, that's easy. I say, okay, you guys are all supposed to know CS1. Let me give you an assignment that involves CS1 concepts. And do that while I start teaching 401 concepts. So my belief was, and this worked fine for grad students, that go look at some tutorials on the web. Okay, and so I give them the NIO assignment. I understood NIO by looking at a particular tutorial. So why don't you guys look at the tutorial too and implement it while I go and start teaching you things. Okay, and that worked fine for grad students for reasons that I don't completely understand, but I try to get a handle on. That was not an easy task. Well, for some students they said, oh, we did it in 4 hours. And some students could never do it. And so I've all winter break I've been thinking about what to do about this, and since I've come back I've also been thinking about this, and I think just before class I finally got it, understood exactly how what I will do to avoid the problem. So my first assignment, that's why I haven't quite posted the first assignment, okay, and that's because that's also the reason why I haven't posted anything. I've just been obsessed with assignment 1. But I think I've got a handle on it, and I hope to finish writing it by tonight, and maybe there'll be snow and there'll be no, but tomorrow will be a holiday. I'll finish writing it up tomorrow. But I promise you before Thursday class, you'll have the assignment. Okay? Assignment will be very long, because I'll tell you how to do it. Okay? And so that's something I need to do this semester. Assignment 6, that consensus algorithm stuff, I put in the end. Students wanted it, and I wanted to learn about it. So having put the consensus stuff, assignment 5 there, I want to revisit assignment 3, and so that will require some work. What we did last time, and what we did with grad students also was, and I think it's a good exercise, that the way you submitted your assignments, you submitted the code, of course, but you also created a demo. You created a video of your demo. Okay? This is a visual program. You can visually show many aspects of what you did. And I had an undergrad student grade those requirements. Okay? In fact, that was a 401 student who was a freshman, but he was a very smart student. And without taking the class, he was actually grading the class pretty well. This time, I have a grad student. And those of you who've done 401 with me recently, I've started automatically grading those assignments. I'd like to do that here, so that's going to be part of what I'm going to try to do this semester is auto grading. And auto grading is easy for me, of course. I mean, it makes our task easier. But can you imagine why auto-grading is good for you guys too? Feedback quicker. You can just, you know what's expected. So if I can have the auto-grader run before you submit the assignment. Okay. So I want to change the assignment so that the assignments won't change fundamentally, but just put some requirements that allow them to do auto-grade. I don't promise that will happen. Whenever we write code, who knows how long it will take to write. But I think we can do it. The code you will write, if you've done at least 401 with me, and especially I'm becoming easier in my old age. So 401 this semester was much easier than 401 earlier. But 401 required more code than this course. Okay, that's a good news. But it'll be complex code. It's distributed debugging. Just as 401 and CS1 really taught you debugging on a single computer. This is going to teach you distributed debugging. Okay, that's sort of. So it's not going to be that easy, but you're not having to debug a lot of code. Okay, so it's like an algorithm course almost. Complex stuff, complex only because it involves multiple computers. Okay, so that's the one skill that I guarantee you will build. Okay, questions? Okay, no textbook. So how are we going to cope? So as you know, I have some PowerPoints and I have PowerPoints from previous courses too. That is just fine. So I will of course publish. So there's two philosophies. Some faculty members don't like to publish material that they use in class, and the argument is, oh, why would people come to class if we just post the material? And why is coming to class important? Well, every study or lots of studies tell you, and intuitively that makes sense. By coming to class, you guarantee that you learn something in that 1 hour. If you don't come to class, you may never learn stuff like that. You may never find out. Okay? So I'm going to do everything possible to encourage attendance. I used to not do it. I said, if I can't hold your attention, if I can't add enough to the material I already have, then what purpose am I serving? And I had lots of students who never came to class do well in that. But lots of students just totally fail class too. And that's because I believe they just didn't put the time. So we will give you incentives to come to class, but I will have the PDF of slides. Plus I will put the PowerPoint, the raw PowerPoint. Can you guys imagine why the PowerPoint may be more useful than the PDF?
You see the translation.
Sorry?
Sorry, the recordings.
If there's recordings, and even if there's no recordings, animation. Okay. So have you dealt with recordings before on PowerPoint? Which courses?
INLS 161, Information Science.
Okay, good. I am on a crusade to go and get my fellow faculty members record their PowerPoints and publish them. And I've convinced some. I just can't get traction. I don't know why people don't do it. And I've actually gone to Microsoft and helped move this thing forward, and yet people don't use it. So I use it a lot. It's got problems. Okay, what we are recording today, I don't promise we'll get. PowerPoint will crash, often crashes. So, but it's worth a try. The trouble with PowerPoint though is that you click on PowerPoint and you've got to download the file, and you've got to whereas PDF you just see it in the browser. So if you notice here, those of you who've seen this before, there's a little icon in the slide that says, hey, this is recorded. Okay? And if you have a recorded PowerPoint, how do you make use of the PowerPoint? How did you use it in that course, for instance?
I made a video.
You made a video out of it?
Yes. Yeah.
The instructor didn't make a video?
I uploaded a YouTube video, like using PowerPoint.
Okay. So if you don't, so we're going to have videos too. But with videos, you don't get the slide structure. It's just a linear. You can't go to slide number 25. So here you can go to slide number 25. Okay. And if you anybody, how many of you have taken 401 from me? So you guys know that 401 you can PowerPoint, you can actually play you can just go and play it. Okay, it'll just play with the animation, so you don't have to, and you can go to slide number 25 also. But more important, you can also click on this icon to really play without going to in the play mode. You can just go and click on it, and you see this bar here. You can play the recording without going into the play mode. Okay, so you can actually click on this and get the audio and fast forward it and rewind it. You don't have to really escape. So what happens when you have a recorded PowerPoint is that when you play the PowerPoint, it just plays automatically. Okay, but if you're not in the play mode, if you're just looking at the PowerPoint, you can just click on this and hear the audio, and that's a VCR control which you can escape into. Okay. But you can create recorded YouTube videos, and they are available also. But you don't have structure there. You can't go to slide number 25, okay, unless you sort of just search for it. So I told you I've been working with the Microsoft guys. So the trade-off is that you don't have slide-based browsing. So Office Mix is a way to get both. Okay, so you go on the web, you don't have to go and download the video, but you will get a table of contents. So you see at the bottom a whole bar. You can just click on these bars at the bottom to go to slide 1, slide 2, slide 3, slide 4, and so forth. So you can browse, and you can even go to a table of contents. So you have slide markers, table of contents. You can go to any one slide and start playing things from there. Okay, now I don't know what's happening with Office Mix this year. Either they're totally abandoning it or they're really adopting it, because Mix is going to go away. And if they're really adopting it, it'll become part of PowerPoint. And if they're abandoning it, who knows what's going to happen. Okay? So, but we have recorded videos from before. And so those are accessible. Okay, now the video nature is such that, the microphone is here. If there's a question asked at that end, it's not quite recorded. Okay, so you'll have, hopefully you can make sense of what's going on from the answer that the instructor is giving, but you can't often hear the student answer. Okay, but you can fast forward, and you can get a clue from my answers. It's not perfect, but it's usable. Okay. If I get time, I'll create more written documents also, but some of the concepts, there's written documents, so that's a concise way of learning things. Okay, and also, like I told you, my assignments, assignment 1 is already 13 pages long. Not in terms of what you have to do, but in terms of how you do it. Okay? So I'm trying to make the assignments self-sufficient also. So there'll be enough help, I think. Okay. Okay, given that I have, I'm going to focus mostly on changing assignments and automatic grading, and given that the material is more or less there from previous classes, the first, I'm going to spend at least one more week teaching NIO a little bit more properly, okay? But after that, we have the material. So the question is, what do we do in class, okay? And arguably, if you have all these resources available, what you gain from class is less than what you would gain if you had none of the resources. You still gain. Okay? It's like a live concert versus a recording, right? But the live concert is more important if there's no recording. So the question is, what do we do in class? So we will have live lectures, but only on the new material, and that I hope to cover in the first 2 weeks. Okay. So given there's other material, the people who believe in flipped classes say that go and look at the material at home, and we'll do something else in class. Okay? And that's certainly an option that you guys would have. There are many options. So, I said I still don't quite know how to teach the various courses I've been teaching, and I'm not unusual here. And not only that, as a community, we teachers don't quite know how to teach. Okay, there's just so many ways possible. And in today's world, especially with this whole active learning, flipped classes, emphasis, and all this technology to support that, it's become even a more complex question. Okay? So I'm not going to say I know the exact answer, but I do know things that fail when you go and just use a lecture-based teaching methods. Okay. So so for this flipped class, I tried this out, and the students said, or I noticed that a lot of them had not seen the recordings or read the material. That's because they didn't schedule the time to do so. So that's one problem. And you're welcome to, in the class, come up with headphones and look at the material in class. Okay, that will be an option you'll have. So we'll have some classes where we will have live lectures. When we don't have live lectures, what to do? Well, one of the things you can do is just listen to the recordings in class. Okay? That's one option. Okay. What else can we do? The classic answer is homework. And you're welcome to do homework here. And that's a good thing to do, because you can get help from me, you can get help from each other. And like I said, the amount of code you will write is small. The problems you'll have will be with debugging. Okay? And debugging, often you need help from somebody else. Okay? And especially if you're using Gypsy, which is a system I built, my input might be useful. Okay? So, but the flip side there is, people say, oh, that requires deep thinking, and there's all this noise, I can't think. Okay, I've heard that too. So if you don't want to do, you want to do homework at home, that's fine, do something else. And, some people work with others and some don't. Okay. So, but you can certainly do debugging, and I really encourage you to do debugging here. Okay, so if I'm going to have you guys watch videos or look at material, I'll just take one more minute. I do want to make sure you understand the material, so we'll have quizzes. Okay, and the good news about quizzes is that you'll get credit for them, and also, but it's not going to be a high pressure situation. There'll be no time pressure. You can finish the quiz around the same time as the assignment is due. Okay, you can look at any material you want to, and you can work with anybody you want. Again, I encourage you guys to do quizzes together, but you're welcome to do it. Okay? So that's yet another activity that you could have in class. Okay? So choice is good, but choice can paralyze. And we'll talk about, I thought I would wrap this all up today, but we'll continue on Tuesday. But I promise you, by next class, I'll have the assignment ready, I'll have the web page ready, I'll have a lot of the material I have here is in the course syllabus. I've written that, I just haven't posted it. I think I haven't updated it. So that stuff will be available. And what I encourage you to do is spend the next 2 days installing the software, running the code, and being in a situation to start implementing stuff. Okay? Okay, so we saw that this class is going to be not a traditional lecture class. We will have some lectures, okay, at least for the next 2 weeks, and we've already had 2 lectures earlier than this and 1 lecture today. So, but a lot of the class will not be lectures. And what do you do in class? We saw last time, you can do quizzes, and you can do them collaboratively, open book. You can troubleshoot or implement assignments, and that's going to be particularly important if something in the assignment I've written is not clear, some of the abstractions you're using are not clear. Okay, so this is a chance to get interactively get the information. And if you want to, you can view the PDFs or even listen to the recorded lectures. Okay, so you have a lot of choice, which is always good. Okay, but choice can also paralyze. And we have conferences where there are single session conferences and multi-session conferences. And multi-session conferences are supposed to give you more choice. And what ends up happening is that in single session conferences, everybody attends the whole session. In multi-session conferences, the message being given is that no particular session is so important that you have to attend. So people attend nothing often. So, I have to watch out for that problem, because I'm guilty of that problem myself. So what we're going to do is have progress diaries. Okay, so you should attend, because attending means that you've taken that time to learn the material. But you shouldn't just attend and physically attend. You should mentally attend also. Okay, And how do we ensure that you mentally attend and do something in each section? So I tried this with COM401, and I thought it worked well, at least from the learning point of view, that you describe for each day at least one specific piece of work you did in class. Okay? So if there was a lecture, explain one concept that you learned. Okay? So the bar is not very high. You don't have to go and write down everything you learned, but at least something you learned. Okay? If you did a quiz, explain some concept on which you took the quiz. Okay? If you were troubleshooting assignment, say, well, I got this part of the assignment working, or I tried to get this part working, and this is an issue I faced. And that will be interesting from my point of view to know what those are. And if you listen to a lecture, explain some concept that was presented or discussed. Okay? And we've had good interaction, and I want to encourage more of that. So also in your diary indicate some question that you answered, okay, that you attempted to answer. That means you said something in response to the question. It could be an incorrect answer or a partially correct answer. That doesn't matter. Okay, and you should give the question and the answer. Okay, and the way I've tried this in multiple ways. Tried Sakai postings. They didn't work very well. So what's worked well is to have a running Piazza post that you edit after each lecture. Okay, so there's only one post, and you don't have to go and submit multiple things. And here's an example. So on 11th of January, my activity was that I learned this particular concept. Okay, that a selector can wait on a specific set of NIO operations, whatever that means. And also, there was a question I answered, and the question was why allow multiple pending operations, and this is the answer. Okay, choose this format. I plan to do some automatic processing of the diaries on Piazza. In fact, one of my goals is to do much more automatic processing of Piazza so that certain answers can be given automatically. That's in the spirit of all this machine learning stuff that's happening in natural language understanding. And if you guys want to work on projects on that, there's a lot that can be done, I believe. Okay. Okay, and you can have multiple activities and answers on a specific date, but have at least one activity, and you can have however many questions you answer. Okay, and when I'm doing live lectures, in the last 5 minutes, I'll try to give you time to go and fill up the diary. Okay. You guys like this idea? Who doesn't like it? Who's going to say something about the fact that you don't like it? It's more work. Okay, it's more work for everybody. So you can see that I have some implicit goal in mind. So why do you think this might be useful? Yeah.
For one, you can correct things, like if I say I learned something and what I put down was incorrect, you can be like, hey, that's wrong.
I can say that's wrong. Hopefully I'll say that in class also.
Yeah.
I won't wait. So you might not get that much feedback from me to your diary posts. Okay, I might just be doing a little check saying you actually posted or not. But that's good, So, but hopefully if you gave me an answer, I'll say that immediately. But that's one thing. What else do you think we can benefit? What else are the benefits you think? Yeah. So, this is interesting. Do make this Piazza post visible to the instructors. I would prefer if you make it visible to everybody so that you share. Okay, just as the Google Doc comments are shared, this can be sort of a running set of class notes. I tried that first. I tried Google Doc and said, guys, let's have collaborative class notes. And people didn't enter, so they were not graded. So this is going to be graded. So this is going to encourage you to post more. But yeah. Any other things? Yeah.
I mean, just like you said, it's a reference of what we've done. So it's a good go back to see, to study, used to study, and you have a reflection of what we did every day.
So just a good way of going back and studying. Okay, now, one of the students said that, I'm not taking class notes. Are you posting the slides? And I am. But there is a benefit to taking class notes, right? It goes into your head and it comes out as text. So it went into your head. Okay, and coming out makes it go deeper into your head. Whereas if you just listen and don't answer, especially, it's not that important. It's not that doesn't contribute as much. So, some of you don't answer. Okay, so diaries are particularly good for those of you who are not answering, but who are understanding and learning, who might go and say, here's an issue I faced, and I don't even know. So I'm more interested in the issues you guys point out than in the answers you give, because the answers I hear. The inarticulated issues I'm interested in learning, and the inarticulate things inarticulated verbally concepts that you learned. So what do you think you learned? The question answer stuff is really important for me. Yes, we're going to have exams. And you know how exams are. You get 1 hour and you have a good day. That makes a big difference to your grade. You have a bad day. That makes a big difference to your grade. Whereas every time somebody answers a question, to me that's they're answering an oral exam. And I put a lot of weight on that. So the question answer part is important because I get to know, because I get to basically take an oral exam. And like I said, it doesn't matter whether your answer was wrong. At least I get to see how your mind was working and you made your mind work. Okay. Retain material better. So you're not taking class notes necessarily, but at the end, if you can just summarize what you learned, then you'll remember perhaps better. And often I'm asked to write letters, and whether it's IBM or Cisco or Google, they'll always have evaluate written skills and oral skills. And I say, based on the exam, yes, I can do that, but I can't evaluate the oral skills. So if I'm not, and then there was an NSF survey I just filled, and the survey was full of how are you improving articulation in class. And I'm teaching a technical course, so maybe that's not my job, but I think it is. Okay, I think if you want to be leaders, eventually you'll program for a while, but eventually if you want to be leaders, you'll have to be articulate. So that's why I'm doing this. Okay, I feel I'm not doing my job if I'm not letting you test your written and oral skills. Okay, so that's the motivation. Okay, and also towards more oral skills. Even if you're in a technical job and don't do managerial stuff, you will create things and give demos. And giving a demo is not that easy. So all your assignments, please, you'll create a 5-minute or less demo of what you did for 2 reasons. A, we may or may not get our automatic grading stuff working, so at least you can show us what you did. Okay, rather than having a one-on-one demo, you can just show what you did. And if we do auto grading, it helps us catch problems in the auto grader. Okay, and again, I really enjoyed watching these demos. I really see people's personalities flower there, come alive. So do make it less than 5 minutes because they will be graded and looked at, and the TA will have only so much time, or I'll have only so much. So grade distribution, I kind of hinted before at what it might look like. So the midterm will be 25%. The final will be 15%. It's not cumulative final. Okay. The quizzes, 10%. Okay, but again, remember they're open and collaborative. The question answer part will be 5%. The class activity report will be 5%. There'll be 5 required assignments. They are not collaborative, so they are for 40%. And there will be an extra credit component on serialization. So there'll be quizzes that are extra credit, and there'll be assignment that's extra credit, and together they add up to 15%, which is exactly what the final exam is. Okay. Now, if you're shy and don't answer questions, you've got that extra 15% to play around with. Okay. So if you really, really don't want to answer questions, or if you answer questions and find it a pain to go and write down diaries, you're not going to get hurt that much. Okay, because there are other ways in which you can overcome that. So there's this distribution is meant to allow you to succeed. Okay. Questions? So people keep asking, are you going to grade on the curve? Are you going to grade on what basis? And even in a large class, I tend to look at almost every student to see what they've done and what I think they've learned before giving a grade. So I'm not the numbers are important, but they're only that important. But general rule of thumb I take in any class that I teach, there's a lot of assignments. So if you do the assignments, you've met what I thought was the goal of the course. You satisfied the goal of the course. So if you do all the assignments more or less, the required assignments, and you get, around average on the other activities, okay? So if then you will get at least a B. Okay. Now you guys are students who've taken operating systems or networking. I'm getting the cream. Okay, I'm assuming that. So expect good grades if you do the work. On the other hand, because many of you are seniors and hunting for jobs and you're kind of tired and grades matter only so much now, I expect some of you to not work as much. So the grade will depend completely on how much you work. It won't be so much an IQ test, okay, just because of assignments and other activities. Okay? But you have to do well in the midterm and or the final to really get a good grade. Okay. Questions? So, there is the sort of classic approach, which in computer science systems courses is never really followed. But the classic approach is live lectures and exams. And this is sort of a really mixed mode where you have live lectures and exams and quizzes, assignments, and diaries. Okay? And hopefully you're learning more there's more active learning in the second approach. And so more learning. But here's a sort of trick question. Which approach do you think is going to frustrate you more? Even at the end of the course, which approach might make you feel overall more frustrated? Yeah.
I guess the mixed mode is not quite as cut and dry. It might not be as clear.
May not be clear and vague and ambiguous, so that'll leave you frustrated. That'll be really bad frustration. Yeah. Hopefully we can overcome that problems with enough interaction. Yeah.
So I think it depends on your individual situation. Because a lot of the times in traditional classrooms, you feel like you may know the material, but because you have a limited opportunity to prove that you know the material, you might mess up on an exam and your grade isn't reflective of what you really took out of the class. But here, there's more ways to spread out.
So which do you think that you're right? One is concentrated frustration, one is distributed frustration. What do you think is going to cause more frustration overall? You like that better, but the mixed mode means you're continuously frustrated. So I don't know. I mean, this is a psychology test. We can do studies on this. So let me tell you from my point of view, live lectures is fantastic. Okay, it's interest from effort point of view. Okay, I'm not saying I want to put low effort, but if I was trying to put low effort, live lectures is great. When I didn't record lectures, my rule of thumb was for every 1 hour of lecture, I had to go and prepare for 3 hours before the lecture, even if I've taught the course 20 times, just so that I know what questions I'll ask, where I'll stumble, where I'll make mistakes so that people correct them. But with recorded lectures, I put it on in the morning while having breakfast, I listen to the lecture, and I implicitly give the same lecture later, and it's just 1 hour of work, and it goes very smoothly. Okay, and I've been doing that for a long time. But the 1 or 2 or 3 exams, they'll show the gaps of retention and understanding, and you have the illusion of actual understanding. You're listening passively, you think you're understanding it, nobody's really testing you whether you understood it, so it's not daily frustration. In active learning, it's continuous demonstration, but you're also continuously fixing these problems, so it's at the end of the course you may feel less comfortable. Okay. And I was thinking about this winter break, and at the same time I was thinking of listening to a podcast. And if you haven't seen this, you should. It was about frustration versus creativity. And this guy starts off talking about this pianist who was invited in Germany by a teenager to give a recital. And is that what you say when you play the piano, recital? Okay, a performance. And the day before, the pianist discovers that the acoustics are all wrong, the piano is all wrong, and wants to not give the concert. And she pleads and says, look, this is the first time I'm organizing it. For my sake, do it. And then he plays the next day. And that is the best-selling solo piece ever. Because he overcame the problems in a very novel way that made it very interesting. Okay? So initially he was frustrated, but that turned out to be a win. Then they did some studies, and they gave students instructions, one in very nice font and one in very obscure font. Okay, since this goes along with what you were saying, that the instructions may not be clear, right? So you would think that studying from the clearer font would be more effective, but according to the studies, and studies have problems, looking at the worse font resulted in better results. Okay. They divided groups into, they had group-based learning, and in one group you interacted with your friends and you came up with some solutions. In others you interacted with strangers. The ones who interacted with their friends had a really good time, were confident about their answers, even though they were wrong. The ones that worked in diverse groups had better answers, but did not have such a great time, and were more unsure about themselves. And sometimes being unsure is good. It means you know what you don't know. Okay? You know, this might cause more frustration. But based on my experience, I feel people learned more this way. Okay? And it's really frustrating to me. This is the most frustrating part. I ask a question, you answer it, then I go and refer to the same question 2 days later. Not only does the rest of the class not remember the question and answer, but the person who answered it also doesn't remember. And you say, oh, how do I have a conversation if you don't remember what I did last time? And you guys are being bombarded with all kinds of information, so it's hard to retain things. So it's my selfish interest from my course point of view to make things stick. Okay, so this is all to make things stick. Okay. On a little tangential approach, so one of the things you can do is talk to each other. And I said the assignments are individual. I got a couple of slides mixed in order. I'm going to come back to that point again. You can discuss solutions with each other at high level. Just don't share code. And this is a rule you learned in other courses also. But certainly help each other with debugging. Okay. And also the assignments may contain solution in English, and read only if stuck.